Hi, my name is Julio Fajardo. I'm with the Turing Research Laboratory from Galileo University in Guatemala City and with the Department of Computer Engineering and Industrial Automation from the School of Electrical and Computer Engineering at the University of Campinas, Sao Paulo, Brazil. I will be presenting in the name of my colleagues Juan Diego Cardona, Guillermo Maldonado, and Enrique Romer, our work for AAM 2020 titled A Robust H-Infinity Full State Observer for Under-tendon-driven Prosthetic Hands. This is the agenda of my presentation. First, I will give you an overview about the problem that then I'm going to describe the under-tendon-driven machine used to drive fingers of an under-actuated prosthetic hand, as well as the problem statement of our contribution. Then I will be talking about the design of the discrete time H-infinity observer-based filter used to estimate the full state of our simplified system and how to derive the observer gain matrix through the use of linear matrix inequalities methodologies. Finally, results and conclusions about our work will be presented. Common approaches to determine useful parameters for upper limb prosthesis involve using different kinds of sensors, such as quadrature encoders, to measure angular displacement and velocity of the gearhead of a DC motor, for example. However, this increases the size, weight, and cost of the device, reducing affordability or even usability. To mitigate these issues, most typical solutions rely on the use of sensorless observers, which estimate the full state of the system depending on the current or voltage measurements. Sensorless observers are typically divided in two groups. The first one estimates the angular speed of the shaft based on the ripple component of the measured signal. The second one are based on the dynamic linear model of brushed DC motors, specifically based on stochastic dynamical system, such as the Kalman filter and its respective variations. However, these errors need to be modeled as Gaussian white noise, which cause some issues in real applications. Here, we present an H-infinity full state observer to gather this data without making any assumption about noise, but only requiring to be energy bounded. This is achieved by measuring the current demanded by the brushed DC motors, actuating the fingers, the prosthetic hand, and using this data to estimate the angular displacement and velocity of the gearhead, which allows to later estimate the generalized coordinates and joint torques as well. In addition to that, the implemented method guarantees the asymptotic stability of the error estimation by solving an optimization problem restricted by linear matrix inequalities using inferior point methods. In summary, we are dealing with the problem of robust filtering for sensorless estimation of a simplified model of a finger with unknown process and measurement noises, but with energy-bounded noise signals. In this way, we propose a linear matrix inequalities (LMI) approach solved using semi-definite programming techniques, taking advantage that the H-infinity norm of the transfer function from the input noises to the estimation error is limited by an upper bound limit called the robustness level. This approach we are approximating to this supremum from the top. The sensorless observer was designed for the fingers of the Galileo hand, which behaves like an under-tendon-driven system. That is, the underactuated fingers behave according to the following equations. This results in a system as shown on this image, with 3 degrees of freedoms and 1 degree of actuation. Also, this system consists in an active tendon to close the finger and a passive one to open the finger. Thus, estimating the angular displacement of the motor's gearhead, one can derive the generalized coordinates and the joint torques of the system. However, the resulting system is computationally too complex to be solved by the means of a compact and simple microcontroller unit. That is why the under-tendon-driven system was modeled as a linear mass spring one instead. This behavior can be represented in the space state with these expressions. This reduces the computational load significantly and permits to estimate theta and theta dot in the embedded system inside the prosthesis. Later, that system must be discretized and the noise components needs to be considered. Then, by defining a general noise vector, the observer base filter can be described by the following expression. Thus, one can determine the filtering error dynamics as follows. The H-infinity norm of the augmented system can be characterized using a Lyapunov function, imposing that if the matrix P is positive definite, the H-infinity norm remains under the value of gamma, taking into account that the energy gain from the noise inputs to the estimation error ratio is less or equal than the robustness level. In this way, the observer gain matrix is obtained by solving this optimization problem, where we are looking for the minimum gamma restricted by this LMI, where C and P are variables of the problem and G is a slack variable that increases the robustness of the observer. Finally, the observer gain matrix can be recovered using this expression. This optimization problem was solved by using MATLAB, MOSEC as a solver, and JORMIP as a parser, and was later implemented in the ARM Cortex-M4 microcontroller used to control the Galileo hand. Together with an on-off current controller to close the index finger and a PID controller to open it, the following behavior was observed, where theta hat, the red dotted line, is the estimation of the angular displacement of the gearhead. Besides, the ground truth was obtained using a quadrature encoder attached to the axis of the motor. One can notice the closing, resting, and opening process estimated from the current measured from the motor's armature with the on-chip analog to digital converter. On the upper graph, one can also notice the efficiency of the model to handle the noise component of the current, as well as the deviation from its ground truth that is not too significant to affect the behavior of the fingers. In addition to that, this graph shows the estimation of the generalized coordinates during the flexion process of the finger. The estimation is on the left side and the ground truth on the right. Moreover, this graph shows the behavior of the estimated torques for each joint, as well as the active and passive tensile forces of the under-tendon-driven mechanism. This shows to be a successful alternative to estimate the states of the fingers in a sensorless way, since the root mean square error of theta is very small. This is sufficient to complete activities of daily living, and this leads to a good estimation of the dynamics of each finger with the aim to implement robust controllers for the flexion and extension processes of the fingers. Thank you very much and enjoy the conference.